Okay, guys, in this video, I want to teach you how parametric equations can be used to model circles and ellipses. And then this kind of opens up a bunch of applications for parametric equations because they can be used to simulate the motion of a particle along a path. So if we start with the basic parametric equations, x equals a cosine t and y equals a sine t. If we solve the first one for cosine, you would have x over a equals cosine t, and the second one, y over a equals sine t. Okay, if you remember the Pythagorean theorem, Pythagorean identity, sine squared t plus cosine squared t equals 1. If I square both of these, okay, I can add them together and equal 1. So sine squared t is equal to y squared over a squared. Cosine t is equal to x squared over a squared. And that's equal to 1. If I multiply both sides by a squared, I would have y squared plus x squared equals a squared. And if you recall, y squared plus x squared equals a squared is the Cartesian equation for a circle of radius a centered at the origin. Okay, so let's see what we can do with this. Now we want to describe the graph of the relation determined by x equals 3 cosine t and y equals 3 sine t for 0 to 2 pi. We want to find the initial and terminal points, if any, and indicate the direction in which the curve is traced. And then we want to find a Cartesian equation for a curve that contains the parameterized curve. Now, in the previous video, I showed you how to do this with a graphing calculator. So I'll assume we know how to put it in parametric mode. All right, so the x is 3 cosine t. Not alpha, t, okay? And again, make sure you're in radian mode here, 3 sine t for your angle measure. Window, we're going to go from 0. Now it's already set up at 2 pi. Whenever you do zoom 6, that's the standard viewing window for parametric equations. Now I'm going to hit graph. I want to show you something. Notice that the initial point started here at 3, 0, and it's graphing it counterclockwise. See how it's graphing counterclockwise? Now, something with this viewing window that does not look like a circle, and I just told you that this should be basically a circle of radius 3. That's because the viewing window, it goes from -10 to 10 on the x and y axes, but the window is distorted because it's rectangular. If I hit zoom square, that's choice number 5, it'll square up the viewing window, and this will look a lot more like a circle. Now, going from 0 to 2 pi, the initial point is 3, 0, because this is basically a circle of radius 3. It's tracing the curve counterclockwise. The terminal point is also 3, 0. Now, in Desmos, real quick, if I have 3 cosine t, 3 sine t, notice it only did part of it. Now, what you can do to get the parameterization here is just put in more numbers. So 2, 2.5, 3, 4, 3, 4, 5, 6, and then 2 pi. And you'll see that the initial point was at 3, 0 right here, and it traced the curve counterclockwise, and the terminal point was also at 3, 0. In Desmos, it'll just graph it all at once. It won't show the tracing of it, but if you use your interval to kind of force it, notice how I went from 0 to 1, and then I went 0 to 2 to 3, 4, and that way we got the parameterization for that one. Okay, so now getting the Cartesian coordinates, you just solve for cosine, solve for sine, And then we know that cosine squared plus sine squared is going to equal 1. So x squared over 9 plus y squared over 9 equals 1. And you could write that as x squared plus y squared equals 9. And just know that the 9, if you think of it in terms of a number squared, which came from 3 squared, tells you the radius of the circle. Remember, a radius, a circle centered at the origin has the form x squared plus y squared equals radius squared. Okay. Now, next thing we want to do is a parameterization of an ellipse. So parameterizations of ellipses are similar to that of circles. Before I get into this example, I just want to talk a little bit about ellipses. Ellipses have a similar form to circles, except they're x squared over a squared plus y squared over b squared equals 1. The distinction here is that x squared and y squared are not over a common denominator, and that's what kind of distorts the ellipse type of, or distorts the circle to make it more of an oval, or more specifically an ellipse shape. All right, so we want to describe the graph of this relation determined by 5 cosine t and y equals 4 sine t from 0 to 2 pi. Again, we're going to find the initial and terminal points and indicate the direction in which the curve is traced. Now, if we go to the y equals menu and put in 5 cosine t and 4 sine t, we're going to do zoom. Actually, let's check the window. 0 to 2 pi, we're good there. We're going to do zoom 5, which is square. Notice the initial point was at 5, 0. It's beginning to trace it counterclockwise, and it's an ellipse. The y-axis point is 0, 4. Then it passes through the point -5, 0. Then the point 0, -4. And then the terminal point is the same as the initial point. And the ellipse is traced 1 time with this parameterization. Okay. Again, if we check it out in Desmos, what was it? It's 5 cosine t and 4 sine t. Again, if we go 1, 2, 3, 4, 5, 2 pi, you get the whole ellipse. And you can again see that the initial point right here is 5, 0. All right, and then it passes through the y-axis at 0, 4, back again at the x-axis at -5, 0, the y-axis again at 0, -4, and then the terminal point is the same as the initial point. All right, and then finally, we just want to get the Cartesian equation. If I solve the first one, x over 5 equals cosine t, and then the second one, y over 4 equals sine t, I square them, and then I add them together. Cosine squared plus sine squared equals 1. And cosine squared is the same as x squared over 25, or over 5 squared. You can write it either way. And y squared over 16, or 4 squared. And this would be the Cartesian equation for the ellipse. All right, guys, hope that was helpful to you with parameterizing circles and ellipses. Take care.